Okay, we are doing section 5.3, which is inverse functions. So remember that we have to do f of g of x and g of f of x if two functions are inverse of each other, and they have to come out as x both times. So to show that the functions are inverses, you need to do the composition both ways. So if we start with f of g of x, that would be placing g into the x in f of x. So 2 times the cubed root of x squared plus 1 over 2, quantity cubed minus 1. We want to do some canceling to simplify. The cubed root and the cube are going to cancel, so we have 2 times x plus 1 over 2 minus 1. The 2's are going to cancel, so we have x plus 1 minus 1, which is x. So we're good that way. Then we have to do the composition the other way. G of f of x. Put g in, you put f into g wherever there's an x. So the cubed root of 2x cubed minus 1 plus 1 over 2. The 1's on top cancel first. 2x cubed over 2. The 2's cancel. Cubed root of x cubed is x. So that way works too. A function has an inverse if and only if it is 1 to 1, which means that it passes the horizontal line test. Or if f is strictly monotonic on its entire domain, then it is 1 to 1. Monotonic means that it either increases the whole time or decreases the whole time. Which of the functions has an inverse function? So we need to graph them first. Let's see if they pass the horizontal line test. All right, for A, looks like that. And if we put a horizontal line anywhere through this function, does it pass? Looks like it's going to. So that one does. It's also increasing over its entire domain. Which is the definition of monotonic, which means that it does have an inverse. Okay, let's do the other one. Okay, not exactly like that, but it looks very similar. Horizontal line test. That time we hit in 3 spots. So we can say that it doesn't pass the horizontal line test. Which means it's not 1 to 1. Which means it has no inverse. Okay, finding an inverse function. First we have to figure out whether or not it has one, and then what we're going to do is change the x and the y's, and then solve it for y. And then you can verify at the end by doing the composition both ways like we did earlier. To find the inverse function, well, f of x is the same thing as y, and then what you need to do is switch the x and the y, and solve it for y. So we need to square both sides, add 3, divide by 2. So x squared plus 3 over 2 is the inverse. Show that the sine function is not 1 to 1 on the entire real line. This is 9. Then show that from negative pi over 2 to positive pi over 2 is the largest interval, which is centered at the origin, for which f is strictly monotonic. So first I'm going to do a little sketch of the sine function. Okay, so we can just go ahead and see right away that if I was to do a horizontal line test, it would not pass. Okay, and then we want to show that it's strictly monotonic from negative pi over 2 to pi over 2. Well, we know that something is monotonic if it's either increasing or decreasing the entire time. So one way to see when we're increasing or decreasing is to find the derivative, which is cosine x. And then from negative pi over 2 to pi over 2, we want to see if there are any extrema in between there. Because if there are any extrema, then it would have changed direction. And if we tested, there's no critical points. So if we tested, we can see that cosine is positive the whole time from negative pi over 2 to positive pi over 2. So it's monotonic, increasing. It could be monotonic increasing or decreasing, so I wanted to be a little more specific. The left endpoint and the right endpoint are extrema. There aren't any other ones in the middle. So we know we're increasing. From negative pi over 2 to positive pi over 2 the whole time. Okay. This part's a little bit tricky. We have the derivative of an inverse function. There's another definition that I think is going to be a little bit easier to understand. And we're going to use this red one over here. d dx of f inverse, so that's the derivative of the inverse, is 1 over f prime of f inverse. Make sure we see that prime there. Okay, so the first thing that we need to do to evaluate that definition is part A, figure out what the value of the inverse is when x is 3. So the easiest way to do that is to figure out when f of x is equal to 3. So we're going to set our original function equal to 3 and figure out when that happens. That happens at x is 2. So when f of 2 is 3, inversely, f inverse of 3 is 2. We know that every time we have an inverse, the x and the y are going to switch. So that's the easiest way to figure out the value of the inverse when x is 3 is by doing what we just did. Then what we're going to do is follow our definition, which is 1 over f prime of f inverse of 3, which is 1 over f prime of 2, because we know that the f inverse of 3 is 2. So now we need to find the derivative. Which is 3/4 x squared plus 1. And then we're going to evaluate that at 2. So what we're really doing is we found 1/4. That was what we had to do. Okay, so what you want to do when you find the derivative of an inverse is always do that first step because it makes it way easier. Unless they already give you the derivative of the inverse, which we did not have. In this case, they do give you the inverse. They give you both functions, so this is not going to be that bad. What we want to do is show that the slopes of the graphs of f and f inverse are reciprocals. So if we have slope at 2, 4, we're going to put that into the derivative of f, which is 2x. So 2 times 2, or 4. And then we're also going to look at the slope of the other point, 4, 2, at the derivative of the inverse. And we're going to plug that in. It's 1 over 2 times the square root of 4, which is 1/4. So they are reciprocals in that point. Then the next one, slope at 3, 9, again into the derivative of the original. 2 times 3, or 6. And then the derivative, the slope at the other point is the derivative of the inverse of 9, which is 1 over 2 times the square root of 9, or 1/6. So we have done our job. And that was section 3 on inverse functions.